something that would include all our...
All right, good evening, everyone. Just as everyone gets settled in, I'm going to go over some announcements and then what we're going to be doing in today's lecture, and probably clearing up a lot of your questions regarding what is this course, what am I doing for Design Activity 2, what can I do as a redesign for the component on the internal combustion engine. On that note, there's a few familiar faces, many of you, but also there's some new faces that I'm seeing. So if you intend to take the course, that's great. I'm happy. I'm sure you're going to enjoy it. However, this course is based on projects and collaboration. So those of you who were here last week, please be friendly to those newcomers. And if they want to or ask to join your group and you have a spot for them, then that would make life a lot easier. If you need help getting up to speed and this is your first lecture, send me an email and I can provide you with all the information that you need to know until you get access to Learn. There's a lecture recording from last week on Learn that you can get caught up on your own time as well. So before I get started, I'll ask if there's any questions kind of related to the course in general that people want to ask. Okay. So an agenda of what we're doing in today's lecture. So the first thing is your Design Activity 1, the group selection or the sign-up sheet on Learn to create your groups. Most of you have already done that. Some of you have emailed me your groups and I've populated those for you. It's important that you get that done. The deadline is tomorrow, but I can extend that if need be, and obviously after the fact, if you need to facilitate a change or there's a new person joining your group, I can do that, but you're going to have to email me. You can no longer do it on your own, okay? The second thing that we're going to talk about is we're going to do about an hour and 20 minutes on internal combustion engine theory. So I'm going to talk about, from a very broad perspective, what internal combustion engines are, and then I'm going to go into some topics that effectively give you a crash course in how to design, understand, and simulate the processes inside an internal combustion engine, okay? People dedicate their entire careers to this one topic and a very specific niche of this topic. So just keep in mind that the way that this is given, it's from a very superficial aspect, but in a way that you can utilize it directly for Design Activity 1, okay? That doesn't mean that we're not gonna look at very detailed topics, but in terms of what I can actually present to you, it's fairly limited. The second thing following that is there's going to be a quiz, and it's not really a pop quiz. It's very easy content that's taken from this theory part, and it's almost like you don't really need a background in internal combustion engines. You just need to be able to think critically about the problem. Okay, so the quiz is going to be done on Learn. Once we go through the whole thing, everyone's going to have 10 or 15 minutes to do the quiz. And you can work together on it if you'd like. The way that it's graded, it does count for marks, okay? However, it's somewhat milestone based. If you leave it blank, you get 0. If you get part-way level of understanding, you'll get half the marks for that question. And if you get what I deem to be fully understanding the concept, then you get full marks, okay? So it's kind of graded in that way. Following that, so that's maybe about an hour and a half, an hour and 45 minutes. Following that, you're going to actually be able to get hands-on with the engines, take them apart, so you can dissect them to whatever degree you want. The instructions are in the form of video tutorials on Learn. If you've reviewed those already, great. If not, you can look at them as you take it apart. But you can take it apart, measure the components. There's a whole suite of tools and measuring equipment that we have that you can measure things. And the main goal and objective is to, by the end of this lecture, is to choose a component that you're going to redesign and measure the critical things that you need from it, okay? So whatever you design in CAD and then subsequently analyze, it doesn't have to be a direct digital twin for the component that you're looking at. So I had a group that approached me regarding the fidelity and all the details that are required if you're doing the crankcase with all the cooling fins and all of that. Obviously, the level of detail there is very high and the complexity is high, so I'm not going to expect you to know every little detail if it's not relevant to the full problem, let's say, okay? All the little mounting holes that are not relevant for the cooling, you don't need to worry about. However, if you want to redesign the piston pin, the part that connects the piston to the connecting rod, Okay, if you don't want to, if you say, oh, the diameter of that is not important because I just don't want to measure it, that obviously is a critical oversight. It needs to interface with the piston, and that diameter is very important from a thermal expansion perspective and from a friction perspective. All those things are important. So you're using your judgment there on what you need to measure. Pictures always help. Okay, so definitely a picture is worth a thousand words, so do that. And then that's pretty much it for today in terms of the content. While you're doing that, I'm going to be walking around and checking in with every group. So hopefully you're kind of seated in your groups right now. The class is kind of expanded from what we had last week. So there's 5 or 6 engine kits. So depending on how they get spread out, people can just take them apart and utilize the pieces. As long as everything goes back in the same box, that's okay. All right? So any questions before I get started on the actual theory part of this lecture? Can everyone hear me? Okay. I'm going to try and stay close to the computer because the microphone that's recording the lecture is on the computer. So if you want to go back, and I've had feedback in the past that students really enjoyed understanding things a second time and listening to an explanation of something on Learn, so hopefully the audio comes through clearly here. So in terms of internal combustion engine theory, I'm going to talk about the fundamentals and just lay the groundwork for what is an internal combustion engine, what are the thermodynamic cycles that are present in the conventional engines that we all are somewhat familiar with, and then the various configurations of engines that are common in passenger cars all the way up to sports cars and utility vehicles and commercial vehicles. Then we're going to look at the engine kinematics. So obviously the engine is a dynamic device that's operating by converting reciprocating motion into a rotating motion. Okay, so there's a whole bunch of kinematics surrounding how all the moving parts kind of cooperate dynamically. And then we're going to focus specifically on the 4-stroke Otto cycle. So that's the thermodynamic cycle that many of you probably remember from thermodynamics if you took that in undergrad. However, I'm going to specifically touch on all the concepts here that are important for this course, especially when it comes time to analyze some of these components. So I'm going to talk about the idea of volumetric efficiency, thermal efficiency, the system losses, which is always a question that I have in the presentation, is how can you quantify kind of the effect of friction or parasitic losses or I don't know, pumping work, things like that. That's a good thing that I can ask because it affects almost all the components in the engine. Emissions, obviously that's a very important thing given global warming crisis and things like that. And then finally, we're going to talk about the reason you're using the engine in the first place is to produce useful work. Okay, it's trying to drive some mechanism to do something. Okay, could be an RC vehicle, it could be the garage door motor in your house, it could be the wheels to your car. All right, and then torque and power, those two things, understanding what they are as engineering quantities and how to use them. And then the quiz says 5 minutes, but obviously it could be between 10 and 15 depending on how long it takes. Okay. So now I found from Webster's dictionary, which is also the definition that Poole-Quebec gives in the textbook that's on Learn, regarding how do you define an internal combustion engine. So we kind of went through this thought process last week with each of the individual components, and I forced every group to kind of make a function statement for each of the components. But how do we do that for the entire internal combustion engine? So the way it's defined here is an engine that generates motive power, motive meaning work, and dynamic power, by the burning of gasoline, oil, or any other fuel with air inside the engine. Okay? So we're excluding electrical devices from this because we're talking about a combustion process that's actually producing the work. And then within those types of engines, there is 2 different categories, one that are internal combustion engines and others that are external combustion engines. So if you've ever been to an air show and you've seen an F-16 fighter jet and they fire on the afterburner, that's burning the fuel outside of the engine. Okay, it produces a lot of thrust and a lot of noise and a lot of emissions, but that's a different type of engine that we're not thinking about here. So what is making the work, or what's generating the work? The hot gases produced are being used to drive a piston or to do other work as they expand. Okay, so from a very simplistic point of view, I always want you to connect what we're talking about subsequently to this idea of a combustion process producing hot gases. Those hot gases create pressure when contained, okay, and that pressure when pushing against the surface can produce a force. Okay, that force is useful to us because we can convert it into a rotation, which is then a torque. Okay, so this is very critical in just unpacking and dissecting this definition. Apologies if your understanding level's all the way up here already. I know that it's kind of patronizing for me to describe it like this, but even when you're very experienced with them, breaking it down to this very let's say basic level is a good way to revisit and understand your thinking process. So we also discussed the topics of how each of the components tied into the structural mechanical aspect, the mechatronics, automation and control aspect, thermodynamics and heat transfer, fluid mechanics, and then manufacturing and cost. So we're going to be discussing all the different components individually again in more detail now. So on the right of this slide here, you can see kind of a schematic cutaway of an internal combustion engine. The slides are uploaded to Learn if you can't see it, so if you want to follow along on your laptop. But from a very simplistic point of view, the first thing is the engine block or the crankcase assembly. Those are synonyms for one another, okay? That's effectively the thing that's housing everything. So what I have here is the first component of the engine. So now we're just learning the nomenclature of what we're physically pointing to when we actually look at something on the engine. And then I have different columns here that highlight if it's part of the structural mechanical, the automation and control, the thermodynamic processes, the fluids processes, or the cost, okay? So I think we made the argument last lecture that you can apply all of these categories to every single component, but the ones I have highlighted here are pretty much the most critical ones or the most significant ones. Okay, so obviously the engine block is the foundation for all the other components. So from a structural mechanical perspective, that's probably the most important thing. And we talked about how the cooling fins are on the actual integrated into the block of that air-cooled engine. So from a thermal perspective, that's probably important as well. But if you're making the engine for mass production in a low value added product like a snowblower or a lawnmower or a scooter, clearly cost is just something that's very important. So that could be a driving factor for all of them. The next component was the camshaft, and that's what's highlighted here in B. And that there was a student last week that very astutely said that the automation and control aspect of the camshaft was an important feature of why it does what it does and why it works. Okay, so it's controlling the process of the gas exchange in the engine. It's timing all of the processes of the intake, the expansion, the exhaust, and the power cycles. Okay, that's important. So I would say that that's most likely significantly an automation and control component. However, you need to be able to support the loads. It's a steel component and there's things pushing against it, like the valve actuators, which are called the push rods. You can see this long rod here is pushing against it. So there's going to be things like frictional forces, wear, bending, torsional vibration, all these things that play into structural and mechanical as well. So now the combustion chamber is this little red volume in here. So the piston, which is this part here, we haven't gotten to it yet, but it's pretty much at the top of the combustion cycle here. So all the air that's entrapped here is the combustion chamber. As this crankshaft rotates and the piston comes down, the combustion chamber will expand in volume. Okay, we're going to look at that whole process in a lot more detail in a little bit. But this small volume here is pretty much the smallest volume the combustion chamber will take. So you're taking all of that energy in the form of gasoline, vapor, and air. So you have a hydrocarbon and an oxidizer, and you're compressing it to a very high pressure and temperature into this small volume, and then you're going to do something with it. You're preparing it for ignition, okay? I'll talk about that in more detail in a little bit. So now just to look at all the rest of the components, because they're kind of easy to look at. The connecting rod, which is this component C here, D, apologies, D. So obviously that's transmitting the full force of combustion to the crankshaft. So from a structural mechanical standpoint, that's very important. And from a thermodynamic standpoint, it's also important because of the fact that it's exposed to some pretty high temperatures. So you need to be able to have a material that can tolerate that. The crankcase, which is the E component here, where is that? So the crankcase is effectively the bottom of the engine block, okay? That's somewhat a synonym for the engine block. You can say engine block, you can say crankcase. Sometimes they segregate the two and they say the block is the top half and the crankcase is the bottom half. But don't get really fixated on that nomenclature. The crankshaft is the part that converts the reciprocating motion into the rotary motion, which is this part here. And that is heavily structural in my opinion. There's actually a group that's looking at that for their component redesign. Redesigning the crankshaft to withstand the fatigue duration of an engine that's operating for several years, let's say. G is the cylinder, which is this part here. Okay, it's actually pointing to the back side of the cylinder. The white part is the back side of the cylinder because it's a cutaway of a cylinder. Okay, and once again, exposed to very high temperatures and very high pressures. So thermal and structural requirements are paramount there. H is the exhaust manifold. So there's no real way to tell the difference between H and J. Okay, one is the intake and one is the exhaust. Okay, you don't see any of the other pipe network that connects to these two. If this were in a vehicle, the exhaust would connect to a noise attenuation device like a muffler, okay, to reduce the noise level that's coming out of the engine. An emissions catalyst to actually convert the unburned hydrocarbons into CO2 and H2O. We'll talk about that in a little bit. And then J is the intake part. So because the exhaust is pointed down, that's probably makes sense that it's the exhaust and the intake's pointed up, just because that's the way in a car it works. They don't want to just shoot the exhaust into the air. They kind of want to point it towards the ground so that if there's any soot or particulates or whatever, they just follow the ground. I is the cylinder head here. So I is this one right here. So this darker crosshatch area. And what that does is it houses all of the valve train components, the springs, the valves, the rocker arms, and all the covers and assemblies and stuff that effectively allow the gas exchange process to occur. So the cylinder head forms the top side surface of the combustion chamber. So that's the top of the combustion chamber, as well as all the structural stuff that it has an intricate port network that allows the induction of the intake charge to come in and then the exhaust to go out. We mentioned the intake manifold. K is the oil pan, which is this part here. That just houses the lubrication in the bottom of the engine. That is very much dictated by a fluid requirement. So if you can imagine that engine might be put in a device that moves around, okay? You might leave it on a table and just let it sit there. So the oil is just going to get pumped through the engine and then it's going to splash back down and sit in the oil pan. Nice, kind of like a bathtub, okay? But if any of you have been go-karting, what happens when you put that engine in a go-kart and you go around a turn? What's going to happen to the oil in the sump? Raise your hand and give me an idea. What? Yes, over there. Exactly. So the centrifugal force of the turning force from being in the vehicle will actually force all of the oil to slosh to one side. So now you need to manage that, because if where you're sucking the oil up from doesn't adequately have enough oil volume to suck from, it's just going to suck in air and then the motor is going to lose lubrication. So controlling that sloshing motion is important. So from an oil pan perspective, understanding of the fluid flow is important. Pistons, which is L, or piston if it's a single cylinder engine, So that's the part that slides up and down within the cylinder and forms the bottom surface for the combustion chamber. Okay, it houses the piston rings, which make a very tight seal against the cylinder and allow the sliding surface to actually move without excessive friction. And it also those rings transmit heat to the cylinder walls. So if you think that the piston itself is actually one wall of the combustion chamber, it's getting exposed to a lot of heat, just like the other walls are. Okay, so but it's made out of aluminum, so that's a difficult thing to manage, and it has nowhere really to dissipate the heat other than through the piston rings. The cylinder head has all those fins that are attached to it that it can dissipate the heat to the atmosphere or the ambient condition. But the piston really has nowhere to go, so the rings are the things that really allows it to extract heat. The push rod we already mentioned here, N, that really is only structural mechanical. It's a simple 2-force member where you just have axial forces from the camshaft that are actuating this valve train up here. The valve, which is P, so that's the part that's located inside this spring-looking device here. And that's the part that actually seals, it's the door analogy that I used last week. It seals the flow into and out of the engine, okay? And then in a water-cooled engine, which the ones that you're gonna be dissecting are not, but in your car, most likely you have a water-cooled engine, where there's jackets around the actual outside of the cylinder that are filled with antifreeze and coolant, or propylene glycol or ethylene glycol, depending on where you are in the world. And it allows it to run at a more stable temperature because water is a more efficient heat transfer media than air. So it's effective at transferring heat away to the surroundings. So you heat up the water and then you use a pump to cycle it to this heat exchanger at the front of the vehicle normally that's called a radiator. Okay, these air-cooled engines don't have that, so that's just one extra thing. The water jacket is a very much thermal fluid type device. So I know that was a ton of terminology, but this pictorial image will be useful for you to go back to when you're actually looking at your particular component and understanding how it fits in with the rest of them. Okay, if you got only 10% of what I said, that's okay. So don't feel overwhelmed. Just understand that it's a complex system with a whole bunch of parts that interface with one another, and generally each part has a few categories of, let's say, design criteria that are associated with it. So some of them are highly structural mechanical, some of them are highly fluids and thermal, some of them are highly automation and control. And pretty much all of them are cost driven in a modern world where components need to be cheap so that people can purchase goods. So now we just looked at a single cylinder engine, and what we're going to be looking at for sake of simplicity and the fact that you can actually lift it up and put it on the table because it's lighter is single cylinder engines. However, most automakers, what they do is they have a combustion architecture where they design a single cylinder engine that works well, and then in order to create a power unit that is satisfying the system requirements of moving a vehicle like a small passenger vehicle or a large SUV, generally all they do is they copy and paste that one cylinder into a number of different configurations in a multi-cylinder arrangement. Okay, so you could have a single cylinder, which is A. You could have something like so A is what we're seeing here in the engine that we're looking at. You could have an inline arrangement, which is shown here as an inline 4. So what that means is that the axes of all these cylinders is just parallel with one another, okay? And it's pretty much a flat design where all the cylinders are beside one another in parallel axial form. You could have a V-type configuration where there's some included angle between the cylinders. So imagine if you want more than 4 or 5 or 6 cylinders, you want the engine will get quite long or wide depending on how it's mounted. Okay, so a good way to make the engine more compact is to arrange them in this V-type formation that allows you to stagger the cylinder bore centers. Okay, and this is a V8, V6 engine, I think. V8, yes. So there's 8 cylinders and they're arranged in a V, and the included angle between them can be varying depending on a whole bunch of different factors that we'll talk about. If you want a very low center of gravity, you can actually splay out the angle or expand that angle to be 180 degrees, and that allows the cylinders to be quite low, okay, because you can mount the crankshaft center line lower in the car or the vehicle. And this is called a boxer or horizontally opposed type engine. Some vehicles use this for compactness and low center of gravity. There's other types of engines like E here, which is a W style engine. The reason being is it kind of looks like a W, so it's a V engine effectively with an inline engine in between. So as you're stepping up the cylinder count here, generally the power and torque increase kind of proportionally. F is a very much underutilized or not as common engine, and this is an opposed cylinder engine. So instead of being horizontally opposed and the pistons punching out from the center, as in D here, these are actually fighting against each other, and the combustion chamber is influencing its volume with two pistons that are traveling towards each other and away from each other. So this isn't very common. Yes, question?
Does this one have two crankshafts?
Yes, so there's two crankshafts on this. That's what makes it quite different, okay? And the crankshafts, obviously, in order to drive one mechanism, so generally there's one crankshaft on an engine. That is the output crankshaft. So there's two intermediate crankshafts on this type of engine here, and eventually they'll connect via a gear train, a series of belts, or a drive shaft, or something like that, to be one output shaft that can drive the wheels of a car or something. Finally, this is quite common in airplanes, and I'll ask the question in the class why they might think that's the case. Is this radial type engine? So that uses one crankshaft, but instead of having a V of multi-cylinders, it just copies that V multiple times around the circumference of a circle, okay? So why might you think that would be useful on an aircraft? Yes?
Propellers.
Propellers, okay, what about the propeller makes it useful?
It allows the propellers to rotate properly.
Okay, so generally in an aircraft, the propeller is mounted to the front of the engine, so he's saying that it allows the propellers to rotate properly. We'll talk about that a little bit. Anyone else? Yep. Vibrations, that's one thing that unfortunately we can't go into a ton of detail in this particular lecture, but each of these crankshaft designs have a different harmonic balance and a different torque signature profile depending on how each of these cylinders is firing. Okay, so what you're saying is very true. It can improve or make worse the vibrational aspect of the engine, and you think that, okay, this engine is just firing every, so it's 1, 2, 3, 4, 5, 7. So 1/7 of C at 360 degrees. It's just firing constantly like that. So it's a very equal torque output. So that is true. Yes. Anyone else? Okay. So he's saying it allows it to move forward very easily, and that is true, but maybe what I think he's trying to say is, if you think about a 7-cylinder engine, which is an odd number of cylinders, but let's say it's 7 cylinders, if you wanted to do a V configuration or an inline configuration, that's quite long, okay? And when you're putting that type of engine on an aircraft, it affects the balance forward and aft of the aircraft a lot. So they need to rebalance all of the people and the occupants and all the gear and the luggage inside the aircraft to compensate for that. So you need to put more weight at the back of the aircraft, then you need a more powerful engine to actually lift it off the ground. So if you can make the engine compact in that direction, it has two benefits. It has the weight balance benefit, but also you're kind of unshrouding all of the cylinders to get direct access with the airflow, the incoming airflow. Okay, and that allows them to cool a lot better, especially when you're operating at very high altitudes where the density of the air is very low. Okay. Once again, this is more detail than you all need to know, but it's good that everyone had kind of their own idea of why it's the case. There's really no hard and fast rule what engine works best in a certain type of application. It really depends on a number of different factors. Is there any questions regarding this? No question? Yes. Okay, so think about it like this. If the crankshaft, here I'll point with the mouse so everyone can see. Let's say we're looking at this V engine, okay? You want to hook up a propeller, which is the load, whatever you're trying to do, to the front of the engine here, okay? It's going to start blowing air, and the fact that you're going to start flying through the air, it's going to have air incoming to it. What's going to happen to these back cylinders here that don't have direct communication with the air? They're going to get kind of blocked by the cylinders in front of them. What about the middle cylinders here? Okay, they only have a 50% of their surface area exposed to the free air. However, this radial configuration has a higher percentage of all the cylinders having exposure to the free air. So if you were to redesign the cooling fins on that, you might say, okay, I want to make them really large, but maybe I want to make sure that air can get to every part of the actual cooling fin. Because if there's something stuck against it that air doesn't allow it to travel to, it's causing issues with thermal efficiency. Yes?
That means that it's is it limited for the air engines in the propellers?
I would say it's limited that, but it's definitely more popular for that. Okay, because if you think about the height of this engine, an aircraft is a large vehicle, so the height isn't that important, but as I mentioned, the length is very important because of the weight balance. In a car, however, if you have to put that underneath the hood of a car and your hood needs to be this high, it's going to be quite hard to see over the hood. So generally they want engines that are slightly more compact. Okay, so that's what you're saying is true, yes. Any other questions? These are all really good questions, by the way. Yep.
So for the type, for the radial engine, what's the difference between this one and the probably the earliest engine like the rotary engine?
Great question. So a rotary engine is a different type of engine entirely. The combustion chamber is a different orientation in terms of how there's no piston in a rotary engine. It has what's called a rotor, okay, and it spins. This is very sidebar to the topic. These are all piston configurations. A rotary engine is a different type of engine. Mazda has, I think they have the patent for it, but they've used it for a number of years. We'll talk about the 4-stroke Otto cycle. A rotary engine actually operates on a 2-stroke cycle, okay? And because of that, the emissions aren't great and they're not very popular anymore, okay? But this radial engine is not a rotary engine. Although the words sound similar, they're not the same. Good question. Okay, so now we're looking at a video animation of the engine that we're actually working with, and it's actually showing the kinematic and dynamic behavior of all of the actual components within the engine. So you can see the crankshaft moving the piston up and down via the connecting rod, okay? And then you have this crankcase that encapsulates everything in the cylinder block, and then the cylinder head, which actually houses all the valve train components, okay? And you can see it rotating there. One important thing, we're going to look at this video a few times, and I want people to point out things that they might have questions about, or that's odd, why does it do that? Okay, but you can see how the gear here is rotating the camshaft. I'll go back. There's a gear attached to the crankshaft here that's rotating the camshaft gear, okay, and that is turning the camshaft, which is pushing on these push rods that actually go all the way up to the cylinder head, and they here, if we pause it, if I can pause it. So these push rods here actuate the mechanism. There's a pin here that they pivot on, and they actuate the valve to open and close it, okay? The push rods only open it. I misspoke there. The push rods open it, the spring actually closes it. So there's a spring that you can see there, and that forces it back to its original position. Okay, so I'll ask you a few questions here. You might notice, and you might not really know why, but you might notice that the gear that's attached to the crankshaft, it has a specific diameter, okay? The gear that's interfacing with is a different diameter. Do you think that's by chance, or do you think there's a reason for that? Just raise your hand if you have any idea. There's no wrong answers. Yep. Change the speed, okay, of course, yeah, it's definitely changing the speed. So is it making the speed higher or lower? Lower speed. Okay, great, that's the right answer. Why do you think it needs the lower speed? what is that gear hooked up to? Yes.
We don't want the camshaft, the balls to open the same speed as the
So you said the camshaft operates at the same speed or a lower speed?
Open and lower speed.
Lower speed. Okay, yes, that's very correct. So the camshaft needs to operate at a lower speed. Yes.
You want it at exactly half the speed through the cycle with the intake and exhaust?
Yes, exactly. So because of the thermodynamic cycle, that it takes if you count it, it takes 4 strokes of this piston to see each of these valves move, open, and close once. Okay, that's one complete cycle because it's a 4-cycle engine. So if you want these valves to move up and down once, which is 2 strokes, you need 4 strokes of the rotating assembly, which is the crankshaft. So you want all of the valve train assembly to rotate at half the speed as the rotating assembly of the crankshaft. Okay, we'll talk about that in more detail in a little bit, but this kind of gives you that idea. The next thing is you can clearly see here that the piston, as it's traveling up and down, because the crankshaft is turning, okay, the piston here sweeps between this higher position and this lower position. Okay, it's sweeping all of this volume from top to bottom. So keep that in mind. That movement is what's creating pressure inside the cylinder and actually making the whole gas exchange process happen. Okay, because you're pushing the air out of the cylinder and pulling the air into the cylinder, that's what's actually forcing the air to come in and out. There's no electric fan that's blowing air into the engine. It's literally from this suction and high pressure scenario. So now, based on the question that I just asked you, we're going to look at in very much more detail the 4-stroke Otto cycle. So we'll start with the piston all the way at what's called top dead center. So that's the piston at its highest position, which corresponded to this location here. Okay. Then we start drawing down, and we move to bottom dead center, and we draw all the intake charge in, and then we turn around and we come back up again, all the way to the point where we almost get to top dead center. We're increasing the temperature and pressure here, all the way to the peak, and then we ignite the fuel, the air-fuel mixture, and then now we are in the expansion stroke, and then we're producing usable work right now. And then we get to the bottom of the expansion stroke, and we have all these burnt gases that we want to get rid of. So we're going to push them out now and open the exhaust valve. Okay, so I'm going to talk about that all over again because there's a lot to digest. So that was one cycle totally completed. So I'll go back and start the slide again. So we're inducting air in because we have the intake valve open, and we're pulling down on the cylinder, which creates this negative pressure that forces air into the cylinder. Okay, and we go all the way to the largest amount of volume here at bottom dead center, and then we start compressing the mixture here. We have the intake valve closed because we don't want it to blow back out the intake. We want to capture it inside the cylinder. Okay, and the pressure, temperature starts increasing, and then we ignite the mixture fairly close to top dead center. Okay, the mixture starts to burn. It sweeps through the entire cylinder, and then we're producing usable work. As the piston moves back down, because the pressure and temperature are so high, this is when we're really pushing on the piston. Okay. So this PV diagram, which you see here, the areas that are enveloped in each of these loops can tell you how much work is being done, because work is just force times distance. Okay. What we have here is volume, which is effectively because the bore size is constrained to be the same. The distance is the only thing that's influencing the volume. So when we have force, which is pressure, times volume, times distance, which is volume here, when you divide them both by the bore size, that's what you get. It's just force times distance. So the area inside this is your positive work in this upper loop here. And then the area underneath is your negative work or your pumping work, because that's not doing anything useful. Okay? Does anyone have any questions regarding that? We'll talk a little bit more detail about this in a second. Yep.
The exhaust loop.
Yep.
Does that go up in pressure when it's attached to a turbo?
Great question. So he asked about turbocharging. We're not going to touch on that in this course, but he's asking, does it go up in pressure when you turbocharge? Okay, so think about what the turbocharger is doing. First of all, a turbocharger is a device that increases the pressure going into the cylinder. So instead of the air that's going into here being what's called naturally aspirated or just drawing in from the natural atmosphere, what you're doing is you're implementing a device that acts as a compressor that pre-compresses the air going into the intake. Okay? So what is that going to do to the cylinder pressure? The pressure inside the cylinder. If you start with a higher pressure, what are you going to end up with? Higher or lower? What do you think? If you start with a higher pressure in the cylinder and you compress it, higher. Okay, so the peak of this curve will go up. This is a really excellent question because this is how you can determine the difference between a high performance engine and an economy engine, and how they work in terms of a pressure volume loop. Okay, you can get more usable work out of a higher pressure engine. Okay, so the peak pressure here will go up when you turbocharge, but what happens to the exhaust gas? Okay, the exhaust is once you expel the exhaust gas, that's what's actually driving that compressor that I mentioned that goes into the intake. Okay, so there's a turbine wheel in the exhaust. Sorry, I don't have a picture to demonstrate to you, but maybe I'll bring one next week that you guys can all look at if you want. And so you have a turbine wheel in the exhaust that effectively increases the back pressure in the exhaust. So all of the pressure in this loop will get larger, and that plays a penalty as well. But you have a lot of extra positive work with some more negative work. The net difference, if you do the turbocharging correctly, you could have really high efficiencies, and you could have really high power outputs, and you could have really good gas mileage and economy and emissions and all of that. So outside of the scope of what we want to talk about, but a great question nonetheless. Is there anyone else that's curious about stuff? Yes?
Could you explain what the clearance volume is?
Yeah, okay, so I never actually explained this formula on the bottom. So let's say we are looking at a general engine and we don't really know what any of the dimensions are. Let's just, for sake of argument, say that at top dead center, which is TDC, that's the highest position that the piston actually reaches. It's 1 unit of volume. Could be 1 meter cubed, it could be 1 foot cubed, whatever you want. However, when you go all the way to bottom dead center, it's 10 units of volume. Okay? So there's a ratio between those two that effectively dictate how much compression ratio there is. And that ratio is given by this, CR, or you can also say RC, and that's just the ratio of bottom dead center volume to top dead center volume. Okay? So the bottom dead center volume is your clearance volume plus the swept volume. So we'll go back. The clearance volume is that little red area there that you're seeing, because that's the volume that you're not influencing by the movement of the piston. Okay? The swept volume is however much the piston is moving. So there's a good diagram in Paul Quebec's book that you can look at that in a little more detail. But the swept volume for the engine is just the displacement of the engine. You might have heard that your vehicle might come equipped with a 3-liter engine or a 2-liter engine. That means the swept volume of all the cylinders combined is 2 liters of displacement. Okay? However, the clearance volume might be somewhat smaller. It might be like, 400 centimeters cubed in total. So you can calculate the compression ratio from those numbers. So the compression ratio here, as one might expect, is 10 to 1 because you have 10 units at bottom dead center and 1 unit at top dead center. So you're compressing it as you move the piston up from the bottom. You're compressing it 10 times from its original volume. So we never really we're looking at this process kind of in quasi-static sense. So we're slowing it down as if we had a super slow motion camera, okay? But everything here is occurring with some time associated with it. The combustion process takes time. The scavenging process of the intake and the exhaust, they both take time. And each of those things actually happen most efficiently at a certain speed or frequency. Okay, because of that, the engine naturally breathes better at a certain frequency of operation. Okay, imagine you running on either your bicycle or you're running on a treadmill. Your legs move at a very efficient pace that's kind of linked to your height, okay, and your gait of how much each stride of your motion is, or how big the revolution on the crank of your bicycle is. Similarly, the engine, based on the engine speed, it has what's called a volumetric efficiency. So ideally, when you breathe in, okay, if you breathe into your lungs, it's going to breathe in as much capacity as your lungs have, ideally, in an ideal sense. An engine, however, your lungs don't actually convert 100% of the volume that they have available into breathing in air. Okay, it doesn't work like that exactly. Similarly, an engine, if it's a 3-liter engine, ideally it's going to breathe in 3 liters every 2 cycles. Every 4 strokes of the cycle. Okay, because you breathe in during the intake phase, then you close everything up and you compress it, and then you expand it, and then you expel it, and then you do it all over again. Okay, so the engine doesn't actually breathe in 3 liters all the time. It might breathe in 2.89. So if you perform the V actual, which might be 2.89 over the V theoretical, which is 3, it gives you this volumetric efficiency. So it might be anywhere between 70 and 90%, depending on the style of engine and how good all of the systems are designed. So you can see that depending on the angular frequency that the engine's operating at, you might have this optimum peak that you want to operate the engine at. So in the way that the computers are controlling the actual engine control unit, you might have this map of a performance, a few performance metrics. So on this one axis here, you have this 3-dimensional map that has engine speed on one axis, it has engine load or throttle position on the other axis, and then it has volumetric efficiency on the z-axis. So this is effectively a model that's modeling the breathing behavior of the engine over all of the operating range of the engine, every angular frequency and every throttle position that the user is commanding. So it's kind of similar to your body. How efficient is your body converting oxygen into, or how effectively is your body metabolizing oxygen? It depends on how fast you're running and how much your heart is pumping. Okay, those are two analogies that you can draw. So now we just talked about kind of mechanical or volumetric efficiency. The second thing that we can talk about is thermal efficiency. So you can imagine that if I have, let's say, one bottle, so this is 750 milliliters of fuel. Contained within that fuel is a certain number of BTUs or joules or megajoules of energy. Okay, just like your battery, they might have a certain, in your phone, it might have a certain amount of energy stored within it. Okay, does your device that you're using, does it actually convert all of that potential electrical energy or that potential chemical energy into useful work? I see a lot of people shaking their head no. So if you have 100% of the available chemical energy from the fuel, there's 3 main places that it goes. One of them is obvious, it's going to producing pressure inside the cylinder that's pushing down on the piston, that's producing work. But with that pressure comes excess heat. Okay? That heat is actually just getting spent out the exhaust, it's getting blown out the exhaust, so you're actually heating up the air around you. If you contain a car within a garage for long enough, you'll heat up the garage quite a bit because all the exhaust gases are heating up the garage air. Okay? That is about 1/3 of the energy too. So 1/3 is going to useful work, 1/3 is going to just heating up the exhaust air, and the other thing you're heating up is just the engine itself. So the cooling system of the engine, all the water and heat exchangers associated with it, that's another 1/3. Okay? And then you have about 5% loss to friction. Obviously that depends a lot on the type of engine and the type of lubricants and all of those things, but that's a good approximation. The ideal thermal efficiency that you have is pretty much related to the compression ratio. Okay, so this formula here, it's in the form of 1 minus 1 over the compression ratio to the power of the specific heats, the ratio of the specific heats of the gases that you're using. So if you remember back to thermodynamics, what that means, it's in the textbook if you're concerned with it. And then subtracting 1, that gives you the ideal thermal efficiency. However, once again, we don't actually achieve the ideal thermal efficiency. In actuality, it's a little bit less. So if we look at energy breakdown of the incoming fuel, so here you might have 20 to 30% going to the power output of the engine. And this is as a function of engine speed. The next thing that you have is heating up the coolant, okay? So this is heating up the actual engine itself. So all of the area entrapped within here, which is another 30 to 40% in here. Then you have another 20 to 30% in this part here. Exhaust enthalpy is just heating up the exhaust effectively. So the air that you're expelling out is also hot. And then you have some heat loss to surroundings. So that's just, let's say the radiator losing heat to the surroundings, or the engine losing heat to the surroundings. And then friction itself, which is about 5%. That's all the rotating components that are lubricated with the oil that's in the engine. So because of this, you can see that some of these quantities vary with engine speed. So you can see especially the coolant load and the brake power, they vary with engine speed. Because of that, you might want to operate the engine at a specific speed to obtain maximum efficiency. So if you've ever driven in a car with an automatic transmission, typically it's shifting the gears for you to keep the engine within that operating range that's most efficient. Okay, and it's constantly shifting to do that. And generally it's shifting very early because of the fact that the lower the engine speed, generally the less mechanical losses you have. So we'll talk about that now. System or mechanical losses. So don't really concern yourself with the stuff that's on the left here. It's mainly just for reference. But what we have on the right is engine speed versus FMEP, which is mean effective pressure. It's just an indicator of work. Let's say the amount of work that's being consumed, or energy that's being consumed by any of these different systems. So the first thing is the crankshaft. To rotate the crankshaft, you need to overcome some friction of the bearings and all the lubricant, and the aerodynamic drag of the crankshaft through the cylinder and the crankshaft through the crankcase. All those things amount to this small portion that you see right here. Okay? If you have a water-cooled engine, and an engine that you want to start with a key for your car, let's say with a battery operated ignition, that you can just crank the engine over and it'll start itself, okay? You need two things. You need to be able to charge the battery, and you need to be able to circulate the water through the engine. So generally those are driven via a belt on the front of the engine, okay? And that's what's going to turn this generation device, which they call an alternator, okay? And that's going to charge the battery. And then the water pump is a vane style pump generally that's just going to circulate coolant throughout the engine. So that contributes to another small portion here. The oil pump is what circulates the oil through the engine. That's an even smaller portion because the amount of oil that's in the engine is even less than the amount of water. Okay. The next thing is the mechanical friction from the pistons and the rings. So that's that sliding friction that we were talking about in last lecture, where you have piston inside the cylinder like this, and you have some rings here, and this is moving up and down. Okay, those rings are directly sliding against the cylinder wall. We'll draw it here too so you guys can see. So those rings are directly sliding against the cylinder wall as it reciprocates. There's a lot of energy lost to that. So optimizing the frictional coefficients and the way that everything works in terms of the spring tension of the rings and how much pressure is distributed on the cylinder walls, that's something that automakers focus on years of their development cycles. The final thing is the valve. So you need to actuate the valve up and down, and by actuate I mean you need to overcome the spring that's controlling the valve. So that takes some work, and that work can be quantified here. So you can see in general, as you start increasing engine speed, all of the work that's required to operate all of these systems increases as well. So the lower engine speed that you can operate at, you might make a little bit less power, but your efficiency will be higher because of the fact that all of these losses are less too, proportionally a lot less as well. So that's the important part. So now emissions. Every single modern vehicle, I think newer than 1973, which is older than all of us, I think, has what's called a three-way catalytic converter. Most all cars have this, and what it does is a byproduct of the combustion reaction. So you're taking a hydrocarbon and you're oxidizing it with air. Okay, we didn't really talk about the chemistry of how this is happening because that's kind of outside of the scope of this course, but every fuel burns at a kind of an ideal stoichiometric ratio where everything happens and it's fully consumed. So the amount of fuel that you're coming in gets fully oxidized. Okay, for gasoline, it's about 14.7 to 1. For alcohol, it's a little bit, not a little bit less, about 40% less. It's like 8 to 1. So that means you need 8 parts of air for 1 part of fuel. Okay? That's the mass of the air, not a volumetric basis, it's a mass basis. Okay? So the air-fuel ratio is just that. It's the mass of the air over the mass of the fuel. What also is typically used in automotive and internal combustion engine literature is what's called an equivalence ratio. And that just effectively describes it's normalizing your air-fuel ratio that you're operating at to whatever the stoichiometric ratio is. Okay? So depending on how far you're deviating from that ideal ratio, it's basically a non-dimensional number, which is nice. So why is the equivalence ratio important? Just because this graph here is shown on a graph of equivalence here. So equivalence ratio of 1.0 means that it's fully oxidized and it's perfectly stoichiometric. So you can see here how the emissions for an internal combustion engine would vary with equivalence ratio. So when we're operating a stoichiometric, which during most of operating a vehicle, that's where the engine is targeting, it's because of the fact that the carbon dioxide or carbon monoxide emissions are low when you do that. As soon as you start going rich from that, you very much influence the carbon monoxide and you make it worse. Okay, rich means that there's more fuel. You have more rich in fuel. Lean means you're less or under fueled. Okay, so you're over oxidized. So there's different factors that influence these emissions responses. So hydrocarbons, NOx, which is nitrates of oxygen or NOx emissions, and then CO, which is just carbon monoxide. All of these things are bad for you. That's the main takeaway. It's bad for the environment. It produces greenhouse gases, and when you trap them underneath an ozone, it can really heat up the environment and cause smog and acid rain and a lot of bad things.
Well, we're totally the opposite.
So what we do is we implement what's called a three-way catalyst, and all that is it's a media by which we can facilitate full combustion. If it never happened inside the cylinder, all of this reaction can continue to occur within the exhaust. And we're providing this very porous surface area, and we're providing a lot of it that effectively everything can get converted into CO2 and H2O. Those are the natural byproducts of the internal combustion engine reaction. CO2 and H2O are not harmful, really, to the environment. So, looking at the engine here, we have another schematic of an engine with the exhaust gases coming out the exhaust system here. This is what might be represented as the catalytic converter. We might have an oxygen sensor inside the engine, which is effectively monitoring the current air-fuel ratio of the engine and adjusting the fuel injectors to appropriately deliver the right amount of fuel. Okay, so if we're operating slightly lean and the target is to be perfectly stoichiometric, it's going to add a little bit more fuel. If we're operating slightly rich and the target is stoichiometric, it's going to subtract a little bit of fuel. Okay, so that sensor, there's some time delay because the amount of time it takes for the air to go from the cylinder all the way through to the catalyst, it takes some time. So you need to calibrate that in the actual control algorithm. So it's a feedback mechanism that has some time delay or some latency or lag value. Okay, so now we're going to talk about maybe a more interesting topic, and I'll ask some questions after this if you guys want. Combustion dynamics. So what happens if the combustion process doesn't actually occur properly? Or what happens when it does occur properly first? So what we do is, because I mentioned that it takes time for the actual flame to sweep the cylinder of the air-fuel ratio, or sorry, the air-fuel mixture, what happens is we ignite the mixture a little bit early because we know we want to produce work when the piston is moving down. Just ignore the fact that the pistons in all of these diagrams is in the same position, okay? So we ignite the mixture, so we create this little kernel of burnt gas, okay? And it starts to expand in this hemispherical shape. So this is image 1, this is image 2, and this is image 3, until you fully sweep the entire cylinder, okay? And it's gonna burn all of the gases within the cylinder, okay? But what happens if we have too much temperature, we have too much pressure, we have some really poor fuel, or we have some inhomogeneity in the cylinder? We might have something like this, where there's some rogue event where it's actually igniting somewhere else. Okay, so we've ignited it where it's supposed to with the spark plug, okay, and it starts to increase in pressure and temperature, and what that's doing is it's actually compressing the surrounding fluid too. And then just because there was some dirt in the cylinder, or locally there was a hot spot, it reignited here, okay, and that causes two competing kind of combustion events, and they fight with one another, and what they produce is this kind of red response here that's very erratic and jagged. So I didn't talk about the response of what the pressure and temperature look like, or sorry, what the pressure looks like versus crank angle, but crank angle is just the circumferential position of the crankshaft. So you start somewhere at bottom dead center, and you start increasing the pressure by moving the piston up. So that's what's happening here, until we get all the way to 0, which we're going to call is the top of this, the piston movement, okay? Then we've ignited the mixture, and we actually increase the pressure a lot because the mixture is burning and expanding and producing pressure. And then we will start to release the pressure by moving the piston down, and it produces all this nice work that we can get useful work out of. So this pressure underneath here is what's useful. However, if we don't time it properly, we can increase the pressure too much to the point where we break mechanical components. So if we make the pressure in the cylinder too high, that might break the piston, it might cause too much force in the connecting rod, it might break the crankshaft. So there's a lot of bad things that can happen with this. So this is what's called engine knock. This is when you've already ignited the mixture, but somewhere else there's a small other combustion event that's happening. It could be one, it could be many, it could be very multiple events that are happening, okay? Something that's slightly different but not as common is what's called pre-ignition. So that's how a diesel engine actually operates. It doesn't use a spark plug at all. It just operates on the fact that as you compress the mixture, you're increasing the temperature and pressure to such a point with such a high compression ratio that the mixture just spontaneously combusts. So it initially just ignites on its own. And then if you actually ignite the mixture after that, you're going to cause, once again, a competing flame front and a competing combustion event that can cause this really erratic behavior within the cylinder, and this really breaks components. So that's something we want to avoid as well. So is there any questions regarding this? There's people that dedicate their entire graduate careers, they're just looking at plots like this on engines. Yeah.
When you add diesel to a petrol engine, does that cause engine knock or pre-ignition?
Good question. So when you add diesel to a petrol engine, so a gasoline powered engine, does it cause knock or pre-ignition? So the first thing is you need to think about diesel naturally, because there's no spark plug that's igniting it. It needs to be able to combust at a lower temperature, okay? Because you're pushing against it and compressing it, and there's nothing to actually ignite it. So the temperature that it gets up to in the compression part of the phase needs to be high enough to auto ignite it. So what's called the auto ignition temperature of diesel is a lot lower than gasoline, okay? So if you put gasoline inside a diesel engine, that's what you said?
Both cases.
So if you put gasoline inside a diesel engine, it won't actually run at all, because the auto ignition temperature of gasoline is too high, so it won't actually auto ignite, and you don't have spark plugs to ignite it, so it'll just, you'll start the starter and it'll just make noise and not do anything. However, the other direction, if you put gasoline inside a diesel engine, most likely it will engine knock first and then it might pre-ignite after that. The engine knock will occur as everything starts to heat up. You're going to generate a lot of extra pressure, which is going to not do a ton of useful work. That extra pressure will make extra temperature, and it'll start increasing the temperature of the engine and the cylinder walls and the exhaust valve and the intake valve and the spark plug. And then all of these things are just going to cause enough temperature to spontaneously combust the mixture by pre-igniting it in a subsequent cycle a few seconds or a few minutes down the road. So it might start on diesel fuel. It might run for a few seconds. You might start doing some damage, but you can start driving around, and then you'll probably break something a little bit into using it. So I would avoid doing that, yes. They do have gasoline-powered engines that operate on what's called a diesel cycle, which is compression ignition. So we're only looking at spark ignition engines here, which use a spark plug to ignite the mixture. Diesel engines just compress the mixture and ignite it like that. There is gasoline engines that do that as well. Any other questions on this diagram? Yes?
Well,
That's okay.
I'm curious, how do you
Diesel engines start without a spark plug?
Excellent question. So how do diesel engines start without a spark plug? Because it's so reliant on the temperature being warm in the mixture for it to auto-ignite, they don't start very well at all without a spark plug. So if you've ever tried to start a diesel engine in Canadian winters, they don't start at all, really. Okay? So what they do is they put what's called a heating coil or a glow plug. It literally is this small electrical resistive element that they just basically short circuit, and because of that it glows red hot. Okay, and it's inside the cylinder somewhere around here, let's say where the cursor is there. And what that does is when the engine is cold, that turns on, and that allows the temperature locally in that area to be hot enough to auto-ignite. So it has a spark plug to start off. Once the engine warms up, then you don't need it anymore. Okay, if you're in a warmer climate, they generally don't need it that much. Good question. Anyone else have an interesting question like that? No, there's no bad questions at all, believe me. Yeah.
why diesel engines are larger than petrol engines?
Excellent question. I could take 30 seconds to explain it or 30 minutes, but the main reason is diesel engines are generally for commercial environments where you're using them to carry a lot of payload or tow a large object, let's say. So they need a lot of torque. Because of that, torque is almost directly proportional to the engine displacement, because the amount of air-fuel mixture that you're combusting is proportional to the amount of force that you can put on the pistons, okay? So because of that, if you need to produce a lot of torque, you need a larger engine because you need a larger displacement. They might not be larger in physical size, but generally they have larger displacement. And most of the time that correlates to a larger physical size. Yeah. There's some engines in passenger vehicles that are diesels that are made for high efficiency that don't kind of operate on that same principle. But that's another course on its own. Any other questions? Yep.
In auto ignition, how do you make sure that you have one spark that propagates into a huge one like that instead of small kernels igniting by themselves?
Excellent question. This is actually a really good question. There's a researcher in systems design that works on this for GM. So most modern vehicle, I say modern, but every vehicle in the past 40 years has a feedback system similar to what was in the exhaust to measure the air-fuel ratio. They have what's called a knock sensor. It's effectively a series of small microphones on the engine, and they're listening for this high-frequency ringing noise that you see here. It's actually listening for that directly, okay? As soon as it senses that, it says, okay, we must have some issue with the engine, reduce the output a large amount until we regain proper function, okay? So it has a series of small microphones that detect that resonating frequency of the pressure signal. Does that make sense?
Yeah.
So when you have two competing explosions like that, they're not really explosions, but they're combustion events. When you have two competing combustion events, it rings inside the cylinder in a different frequency. and there's a microphone that reads it and analyzes the signal, post-processes it, and does some decision making based on that. Any other questions? These are all amazing questions and a little bit too complex to do for the mechanical redesign on that particular engine because that doesn't have any of these systems. It's very simple from that perspective. There's no real electronic adjustments to it. Okay, next slide. So this slide is probably going to be useful to a lot of you. From an engine heat transfer perspective, if we look at the steady state temperatures of the components within inside a cross section of the cylinder, we can say, let's start at some of the cooler things and work our way up, or let's start hot and go cold, okay? So on the right, just to kind of amaze you, you can YouTube this if you'd like, but there's a slow motion, I think this is 3,000 or 4,000 frames per second, of a engine with a clear cylinder head, okay? They've modified the cylinder head on this to basically move everything out of the way so you can see the combustion event happening. And the spark plug is a very small little electrode that they have right here, okay? So I don't know, maybe if I shut off the lights, you'll be able to see the valves opening and closing.
I've seen this one.
What?
I've seen this one. The glass cover. I don't know what the other ones were, but they were white.
Okay, so I'll let someone point or try and figure out what was the exhaust valve and what was the intake valve based on how things are moving. Come on. Okay, so which valve is open when the exhaust, when the exhaust is traveling out?
It's the lower.
The lower one, yes. So you can see it's ignited there, the piston is moving down, it's producing usable work, and the lower one here is open, and you actually don't see the flames going out because it's fully burnt. That's good, okay? The flames are only occurring as the combustion event is sweeping the combustion chamber and pushing down on the cylinder. You can actually see small little fuel droplets coming in the intake side here before the spark ignites. I want you to really look at when you see that little spark, okay? Let's go back. So you're gonna see the spark fairly soon here. Okay, in the next cycle you'll see it. So does it happen before or after top dead center here? So the piston's coming up. So did it happen before or after the piston reached top dead center? I see some saying after, some saying before. Before. Okay, that's because of the fact that it takes time for the actual mixture to ignite and start to burn. If we want to push on the piston in the downward part of it, we don't want to start the combustion process in the downward part of it. We want it to already be burning in the downward part of it. So we need to provide that small amount of what's called ignition advance. So that's useful. The other thing is when it actually ignites, you might notice that there's a small amount of delay. It doesn't instantly start flaming, okay? You'll see that in the next cycle again. So you also saw that because this cylinder, this engine is quite rudimentary, it didn't differentiate between one stroke and the other. So you saw it actually sparked on the bottom of another cycle, which wasn't useful. Okay, but because there was no fuel air mixture inside the cylinder, it didn't burn anything. So it sparks no matter what. It sparks on every 2 strokes of the engine. Okay, most simple engines operate like that. Most advanced engines do not, because you can imagine if you're designing a spark plug, you're excessively wasting it by a factor of 2. Okay, so now let's talk about the temperatures, the steady state temperatures of all the components. So, yes, of course.
So in this vehicle, is the oil premixed with air or is it injected in service?
You mean the gas?
The gas.
Yes. So great question. Is the gasoline or the fuel pre-mixed with the air, or is it injected inside the cylinder? So prior to entering the intake valve here, the intake port, there's either a fuel injection system or a carburetor. We discussed this a little bit last lecture, but it's effectively delivering liquid fuel that will vaporize into this port and then travel into the cylinder. Okay, you might notice, as I mentioned, you see fuel droplets here because it's not fully vaporized. That's just because of the fact that it hasn't had enough time and temperature to vaporize, because you need favorable conditions to vaporize a fluid or a liquid, I guess. So you see actual liquid here. The liquid isn't burning, it's only burning the vapor part of it. The liquid is actually going out the exhaust as unburned hydrocarbons, so it's not productive for us. So you want to design the system to vaporize the fuel as good as possible. That'll give you better economy, better emissions, and better power output. That's a win-win. So if you want to work on that, that's a really good thing.
So in modern engines, do we inject gasoline directly inside the chamber or outside the manifold?
Excellent question. So direct injection engines, which effectively, instead of introducing the fuel here, they actually just directly inject it into the cylinder. Okay, so there's some mechanical complexity to that because you're injecting it into a very high pressure, high temperature environment. So that causes a little bit more difficulty with how you're going to do it. However, it allows you to spray the fuel directly where you need it. Okay, instead of relying on the air to bring the fuel into the cylinder, you could just spray it all over the cylinder and get it fully mixed if you want, like that. That's an easier way of doing it. The other thing that it really does is that, let me ask you this. We talked about last lecture, when you vaporize a liquid, what happens?
Surface area.
Surface what, sorry?
Surface area increases.
When you vaporize a fuel, the surface area increases, sure, yes. What happens to the temperature? Decreases, right? So when you vaporize a liquid, the temperature decreases. Coincidentally, maybe not so coincidentally, what is the lowest temperature in all of the ones that's cited here? All over the engine? The intake, okay? That's because this type of engine is vaporizing the fuel in the intake. So we start with air that's coming from outside. It might be 20 or 30 degrees Celsius in the summer. It might be 0 to 5 degrees Celsius in the winter, okay? It's going into the engine, but it's traveling through this hot intake system that's about the temperature of the cylinder wall, which is 185. Okay, this is unfortunately, 185 degrees Celsius is the cylinder wall. The coolant temperature of this engine is 105 degrees Celsius, okay? So that 105 degrees Celsius is taking that air that started at between 0 and 30, okay, and it's heating it up. Okay, it's heating it up not quite to 105 because what we're doing is vaporizing fuel in it that's cooling it down. Okay, that air is coming into the cylinder, it's getting inducted, it's going to get compressed, it's going to get ignited and expanded, and then it's going to get exhausted. So during the combustion process, where's all the heat going? The next hottest thing, or I guess the very much hottest thing, is the exhaust valve. Okay, that's 650 degrees Celsius. The reason for that is all the combustion byproducts, all that high temperature gas, all that high enthalpy exhaust gas is going out the exhaust valve. And it's exposed directly to the combustion temperature, okay? And it has no evaporative cooling that the intake valve sees. That's why the intake valve is only 250 degrees Celsius, because of the fact that we might actually have liquid fuel that's crashing against it, as you see here, okay? So we're not passing any hot gases through the intake valve, and we're actually cooling it with liquid fuel somewhat. You don't get that with direct injection. Instead, what you do is you just spray the fuel into the cylinder, and you can cool off everything in the cylinder if you want, which provides a real benefit in terms of performance and emissions and efficiency. So that's why they're the wave of the future, and they're almost on, I don't know, 50 to 60% of modern vehicles, I would say, have direct injection, because you can cool the cylinder directly. We don't really care about cooling the intake manifold. That's not that important. What else? So the coolant we said was 105. The spark plug, because it needs to effectively ignite the mixture, is quite hot as well. Okay, it's 600 degrees Celsius, but when you spark locally, that area can reach tens of thousands of degrees. Okay, because it's effectively an arc. It's like a mini lightning bolt of energy that's igniting the mixture. The piston face is also exposed directly to the combustion gas, so that's quite hot. It's 300 degrees Celsius. The piston rings are slightly colder because they're touching the cylinder wall, which is only 185 degrees Celsius, because the cylinder walls are cooled by the coolant, which is 100 degrees Celsius. Okay, it's pretty much controlled to be about the boiling point of water. Okay, we raise the boiling point slightly with adding alcohol to it and putting it under pressure, which allows you to operate slightly above boiling and suppress boiling. The piston skirt, which is the lower part of the piston, is only 190 because it's further away from the combustion gases. And then the oil that's all the way at the bottom of the engine is about 70 degrees Celsius, and it's about the same temperature as the intake manifold because it has some airflow that's going around it. So is there any questions regarding this? I'll play the animation one more time while I take some questions. Yeah?
Why is the temperature of cylinder wall so low?
So high?
So low.
Because it's effectively being cooled by the water around the engine. The coolant around the engine is extracting heat away from the cylinder wall. If you look closer to the top of the cylinder, it might be slightly higher. It might be 200 or 300 degrees. So as you get closer to the intake valve, these temperatures might be more similar to one another. But at that location of the cylinder wall, it's not as high. Any other questions? Yes?
How does the intake air temperature affect the efficiency, or if the intake air was a lot hotter than what we expect?
Excellent question. So how does the intake air temperature affect the efficiency? Okay. So what, if you remember from your thermodynamics class, what happens to the density of air with temperature? If you look up the barometric pressure on the weather network, okay, in the winter, is it generally higher than in the summer? Yes, okay, because of the fact that as air contracts when it gets colder, all of the molecules get closer together and the density actually raises 2 or 3%. Because of that, if you're sucking that air into the engine on a volumetric basis, you're sucking 2 to 3% more air molecules into the engine. Because of that, you can inject slightly more fuel and you can get more useful work out of it. So with a cooler intake air temperature, you're going to get a slight amount more work out of the engine. It's useful. The problem is you actually cool all of the temperature in the cylinder gets cooled off a lot too because the coolant is cold as well. If you drive around in the middle of the winter, your car is constantly rejecting heat to the surroundings. So it's a give and take somewhat. Any other questions? That was a very good question. Okay. So now a kinematic force balance on the piston. So if we look at a cutaway again of a cylinder, and if you remember, I promise I'm not going to bore you with formulas here, so it's going to be very simple. If we look at a force balance on the piston, this is directly related to a question on the quiz that I'm going to give you, so just bear with me. You have sigma fx, where x is the direction along the axis of the cylinder, so in this vertical direction here, is equal to mass times acceleration, okay? The mass is just the mass times the mass is just the mass of the piston, but the acceleration is effectively the rate of the displacement of the piston. So U of piston is just the position of the piston. So rate of change of the displacement of the piston is the acceleration, okay? Another way you can write this is equal to sum of the forces. So mass times acceleration, which is this, is equal to the sum of the forces, which, what are the forces acting on this piston? I want people to raise their hand and give me an idea. Yes?
Pressure force and reaction force from the connecting rod.
Okay, good. He said all three. The pressure force, the reaction force from the connecting rod, and the frictional force. Yes. So these three these three boxes here highlight that. Okay. So the gas pressure inside the cylinder. You want to go ahead?
So use the velocity.
Yes, U is the velocity. Yes. So the force inside the cylinder, which is this green area, the force due to the cylinder pressure, which is this green term here, is just the pressure times the area. okay? That's the force here. And is that positive or negative? This is the important part. So if we're in this stroke of the engine where we're producing work, it's positive. By convention, let's say positive is down, okay? If now the connecting rod, what happens when we push down on the piston? The connecting rod's going to push back, okay? And it's going to have a force that's aligned with the axis of the connecting rod. So that blue term, that's the second one that you mentioned here. So all we want to know is the vertical force on the connecting rod, which is just this vertical component of that axial term. So it's just cos theta, which theta is this angle, times the axial force. So whatever the force in the rod is, times cos theta. And because that's pushing up, by convention it's negative because it's not doing useful work, so it's negative. Okay? The final thing is the frictional force, depending on the direction of the friction at that particular time. Generally it's always negative because it's opposing the direction of motion, but I put it as plus or minus here just to show you that it can change direction depending on the direction of motion that you're in. Okay? Hopefully that's simple enough that everyone can understand and appreciate that. Remember theta here, okay? Because the piston at this particular moment in time is at an angle, there is a vertical component to this force, but there's also a horizontal component that's pushing against the cylinder wall. Okay? That's going to wear the cylinder wall out because you're pushing against it all the time. Remember that for the quiz.
Can you say that again? Sorry.
Sure. Just so everyone's on the same playing field here.
Can you please come again? The last statement.
Say it again.
The last statement again.
Okay. So we just talked about where the axial force gets decomposed into a vertical component, which is directly opposing the piston motion, but it's also pushing the cylinder, the piston against the wall of the cylinder. Okay, because this axial force is a vertical component and a horizontal component. This horizontal component is reacted away in this direction of the cylinder and it's going to wear out the cylinder wall. So just remember that.
Side, not both sides.
Think about it like this. So when you're pushing up on the cylinder, it's going to wear out one side. But when you're pushing up, you're not really resisting the combustion forces. You're just pushing against the cylinder pressure. Okay. When it's getting pushed down on, it's going to have a lot more combustion pressure, which means a lot more side loading on the piston. So in one direction, it's going to be more than the other. But it does have a horizontal component regardless of the direction that it's at because of this angle theta. So if you take apart a running engine, you'll notice one side of the piston is always worn out more than the other. Or not a running engine, if you take apart an engine that has been run. So in case some of these terms that make sense, you can see down here what they mean. Okay. As I mentioned, the sign on the friction force depends on the crank angle. So it's always opposing the direction of motion. So we always really say that no matter what, if you just want to look at scalar quantities for all three of these and assign the plus or minus as you go through it, or you can look at a crank angle range between 0 and 180. It's negative, and it's positive between 0 and 180 and 360. So the final thing that we're pretty much going to talk about is engine work. So we talked about torque to some degree, but what does torque actually mean? Okay, how do we get the torque? So as the cylinder starts at bottom dead center here, which is this part of this XY plot, so we're starting right here, okay? The pressure in the cylinder is very low. We start moving up and the pressure starts increasing, almost exponentially, right to the point where we ignite the mixture, and then there's a small delay, and then the pressure starts to rise because the combustion occurs. And we actually time this maximum pressure to be slightly after top dead center. So you can see that that peak is occurring slightly after this dashed line. Why does that happen? This is a difficult question to think about, but I'll give you a very easy analogy to remember it. Yes?
If they have maximum pressure at top dead center, the downward push
Excellent. So it's pretty much exactly what I want to hear, but not exactly. So he said when it's at top dead center directly, the downward pushing force is not directly producing the work it's not pushing directly down. Say it again.
It is pushing directly down, but it won't produce as much torque as when it is pushing when the piston is already on its way.
Okay. So everything is correct except the fact that if you push directly down, you're not producing any torque at all because of the fact that imagine if you were on a bicycle and you had the pedals perfectly aligned up and down. What happens when you press down like that? Nothing. The pedal will just lock there and not move. If you're moving forward fast enough, there's enough inertia in the wheels rotating and everything, it'll actually continue to move. But if you just are stopped on a bicycle and you can actually stand on the pedals with your full body weight and it's not going to move. The similar thing with the engine. If you were to time when you were to push on the pedals to be about 12 to 15 degrees after the peak, that's when it actually does the most amount of work. And the reason for that is the area under here is maximized, okay? If you move this to the left, you're sacrificing all of this area here that is doing useful work. So it's not that good, okay? And the other thing is we get all of this pressure so as the cylinder goes through its expansion stroke, okay, the pressure starts to decay. Then we open the exhaust valve and the pressure pretty much goes out the exhaust and it's gone forever, okay, until the next cycle comes on, okay? So we get all of this work under here where we're exerting pressure on the piston, that's putting a force onto the piston, that's turning the connecting rod. But we had this negative work in the first part here, so the area under the curve here is the negative work that we had to pay to compress the fluid to do the work in the combustion stroke. Question, yes?
Yeah, the actual crank angle, the difference between 0 and the maximum, where the maximum pressure occurs.
Yes.
How do you make that like the maximum? Like, how do you make it so that that angle is the peak?
So you're saying align it with 0?
Right after 0.
Okay, so that's a good question. She's asking, how do you make this maximum pressure be exactly right after 0? So because of the way that the kinematics work out with actually the crank motion, you don't want it to be right after 0. You want it to be about 12 to 15 degrees after 0 because of the fact that the force is not pushing directly down on it. It's pushing the crankshaft through its rotation. It's like pushing on a bike pedal. You don't want to push directly down on it. You want to push it slightly after it reaches the top. So 12 to 15 degrees is what really works for most engines. If you want more detailed explanation on where 12 to 15 came from, I can give that to you. Anyone else? That's a great question. Okay, so we talked about the positive work and the negative work. Now, power is just torque times speed. It's the rate at which you're accomplishing work, okay? Some of the units that you might be familiar with, at least in North America, the way they advertise things, is power is in horsepower and torque is in foot-pounds. Very arbitrary units that have really no meaning or no basis or no scientific explanation, but 1 horsepower is literally the amount of weight that 1 horse could pull in 1 second, 1 foot of distance. So it's not a very useful measurement, but if you look at torque and you're trying to find the rate at which you're accomplishing torque, okay, that is how fast the engine is operating at the given torque level. Okay, so if we have a torque in foot-pounds and we multiply that by the RPM, in order to make the units work out, you have to divide by 5252. I'll describe what that means in a little bit, but that's how you get power. That's the rate at which you're accomplishing work. So power is just torque times the speed. That's all you need to remember, really. So if you remember those performance curves that we had of the engine, let's say I wanted to calculate the power at 2500 RPM, okay? And we can clearly see here that, okay, the top graph shows the torque and the bottom graph shows the power, okay? But however, just from the top graph, if we say at 2500 RPM, which is this line here, we actually have about 14 foot-pounds of torque. That's the axis on the right here, okay? So 14 foot-pounds of torque multiplied by the RPM, which is 2,500, divided by 5252, actually gives you 6.6 horsepower. So if we look at the performance curve here at 2,500 RPM, it's about 6.6 horsepower, which is the scale on the right. So the units check out. It does work. So that pretty much concludes all the theory that you're going to need for the quiz. I'll answer any questions you want now, and if you have more after the quiz, by all means. But yeah, if there's anything I can clarify, if there's anything you want to go back and look at a slide now and talk about in more detail, if there's anything you're interested in for your project, by all means raise your hands, otherwise we can get started on the quiz.
Actually, I have
Sure.
a question. What is the deliverable that we need from the engine? Is it the power or
Good question.
So an excellent question was asked. What is really the deliverable that you need from the engine? What is the reason you're using the engine in the first place? Okay. So he said, is it power or torque? What is desirable from a design perspective? So realistically, torque is what's producing the twisting force that actually moves things. However, you might notice that if you're operating a vehicle on a highway, you're operating at a very high speed. Okay, so the engine is operating at a higher speed because you want to travel fast. So in order to travel fast, you need to accomplish a certain amount of torque at a high engine speed, which means you need to have good power. Okay, so if you want to operate a vehicle at very low speeds or an engine at very low speeds, torque is really all you need. However, if you want to operate it at high speeds, then power is more important. Does that kind of make sense?
yeah, well, as far as I understand, sometimes like when we are going up a ramp, we shift to lower gear because we need more torque.
Yes.
But when we on a highway and we need more speed, we shift for the higher gears, which actually does not give enough as much torque as it did
Yep.
on the ramp. So are we shifting between speed and torque?
Yep.
Like, depending on the circumstance.
So he had an excellent follow-up question. When you drive a vehicle, why does the transmission shift gears to certain ones as you accelerate and then as you cruise down the highway? Okay, the reason being is as you want to accelerate, if we go back to that force balance, instead of on the piston, we're going to look at the whole car. Okay, if we want to accelerate and the mass of the vehicle is constant, we need to apply more force. Okay, that's the only way that we're going to increase the rate of acceleration. In order to apply more force, we need to increase the torque of the engine. Okay, so in order to increase the torque of the engine, we step on the gas pedal. And what does that do? That allows more air to go into the cylinder. It allows more combustion pressure to occur, and then it allows more useful force to get put onto the piston, which turns the crankshaft with more torque. However, what happens if we change down a gear? Okay, we're now going to operate the engine at a slightly higher engine speed, but we have more mechanical advantage in terms of the gear ratio because we might be operating the engine at a certain speed, say 2,000 revolutions per minute, but the wheels are not traveling 2,000 revolutions per minute. They're slower than that. Okay, so we can change down the gear just like you do on a bicycle when you start climbing a hill, because you're commanding that you need more torque to climb the hill. Okay, once you reach flat ground, then you can start increasing the gear, so go up a gear so that the engine speed can go lower. Hopefully that makes sense. And the computer control algorithms that determine the optimum gear number for a particular load scenario and vehicle speed, steering angle, brake position, all those things, it's a very complex algorithm that dictates what transmission gear it should be in. Any other questions? That was a good question. So the engines that you're using don't actually have a gearbox at all. You hook it up directly to whatever it's using. At least internally there's no gearbox. You can put a gearbox on it if you wanted. But if you've ever ridden like an older bicycle or a children's bicycle or a fixie bicycle that has no gears, no changeable gears, you might notice that it's very difficult to climb a hill because whatever torque your legs are able to provide is directly the torque that's being applied to the wheels, multiplied by whatever gear ratio you have in the sprockets. But generally, that's just 1-to-1. So as soon as you need more torque to climb a hill, you can't deliver it. Where on a mountain bike or a road bike, you can just change the gear ratio so that your feet spin faster and you go slightly slower, but you have the torque to climb the hill. Any other questions? Anything I can clarify? I'll talk about after the quiz what you're going to need to do for the presentation and all of that. But before we do the quiz, you guys want to take a break for 5-10 minutes and go to the washroom and stuff? Or are you okay? Yeah? Okay. So we'll break for 5 minutes, and then when you come back, you have about 10 minutes to start the quiz, okay? I'll put up a slide on how to get to it.